In this lab, we're going to build an EKG. The output will look like this when it's functioning. Well, it turns out that we are basically a bag of ions. And when your heart, your muscles move, they move through the movement of ions in and out of the cell, enabling the muscles to contract. And that signal can be detected on the surface of your skin. And we're going to use these sensors here. This is made by Red Dot. I hope you can see this. They've got some adhesive, and on the back there's a little bit of a, it's like a gel contact, and that contacts your skin. And you will put these on various places on your skin. I happen to, in my measurement, put a couple here and then one down here because your heart signal comes across your chest like that. So it comes out pretty strong. But so once you do that, we're going to use these alligator clips to clip onto the electrodes and then hook it up to your circuit. And you'll want to wait till you're ready and know that your circuit's working before you take these off, because these gel electrodes do dry out. Okay, in terms of our iSim idea, let's look at how our measurement is going to happen. We've been focusing earlier on sensing and converting the sensed quantities to a measurement quantity. Now, this lab is a little different in that we're essentially going to kind of mix these two. We're looking for the output that is essentially going to be a voltage with time, and we're really wanting to see, the heartbeat on this axis. Now, in doing this, we're going to focus here on the instrumentation because we need to employ everything that we've learned in order to get this heartbeat information. Let's look back. So we started out with the idea of a voltage divider. So we have a voltage in, and that is dropped over two resistors, and we can measure the voltage out that is essentially dropped over that bottom resistor. Now, what we know is that this being in series, the current that goes through those two resistors, is the same. So we can use this equivalent circuit setup to compute an equivalent resistance that is just the sum of these two resistances. So if we want to, for example, know the current, we know that it's just basically this total voltage drop divided by the total resistance for this current right here. So in the case of when we wanted to figure out what the output voltage was, this output voltage here, it was just equal to the current times this resistance 2. Or for this current, we could just substitute the voltage drop here for the whole circuit, this voltage drop divided by the total resistance. So that's Vin minus 0, divided by the sum of the resistances. So we could substitute this term and then multiply that by R2. Well, that equation turns out to be this equation, where you just set the output voltage equal to the input voltage times essentially the fraction, this R2, of the total resistance. Okay, so that's an easy way to remember this equation, is this output voltage is just the input, or the input times R2 over the total. Now we use that voltage divider concept to work with all our circuits. So we had this basic voltage divider circuit, and then we replaced one of these with a sensor. In lab 1, the resistor that we had, the voltage divider we had, basically was the potentiometer. You might recall this was 0.1 and 0.3, and then there was a point called 0.2. And this potentiometer was basically attached to the shaft of an axis that would rotate like this. And as it rotated, it would move this point up and down this resistor, basically changing the value of this total resistance was the same, but it was changing the V out by changing the point at which it was tapping off the voltage from this drop, 1 volt to 0 volts. So again, the rotating the shaft like this had the effect of moving this needle up and down. So in lab 2, what we did is replaced one of these resistors with a sensor, like a thermistor. And then in lab 3, what we did is we started out with this basic voltage divider idea, and we created two voltage dividers, one here and one here. But in this one, we replaced this leg with our strain gauge as the sensor, and we put a potentiometer in here so we could kind of adjust the resistance to match that one. And if these were perfectly matched, again, this is a 5-volt input. If these were perfectly matched, then this delta V would be nothing because you would drop half the voltage here and the rest of it here. Well, to measure small changes in that delta V, we sent that signal, that output signal, that delta V, to, we sent that to a amplifier that had some sort of gain, and so we got a larger and amplified output from this initial Wheatstone bridge. Okay, so we're still working with this basic circuit here, and then we did the relative humidity, and we made two changes in this measurement. We used a alternating signal instead of a DC signal, and then we replaced one of the resistors with a variable capacitor, which was our relative humidity sensor. Okay, now here we are, and this time what we're going to do is we're going to replace these things, but also this. So in our sensor design, this source of the voltage variation is going to be us. Now, our signal, you'll remember, is going to be a time varying signal. So we're going to design this instrumentation to basically isolate our heartbeat inside this signal. So what we're going to need over here are some filters, and we're going to need an amplifier in order to get a large enough signal. So conceptually, you have two stages of filtering, stage 1 and stage 2. So this will filter and amplify, and we're going to do that again. And you'll see in the instructions, we're recommending that you build one stage at a time, make sure that's working, and then build the second stage onto it. Okay, there's lots of ways that you can do this, obviously, but I just wanted to show you that I laid my circuit out like this. I have stage 1 over here and stage 2 over here. I used some color coding. I used green to indicate a connection to the ground rail, and then white to the 2.5 and red to the 5. And then this purple is in between, just so I could kind of visually distinguish between these. So as you can see, I've got some markers to help me remember where things are connected. But these little header pins work well with the kind of pins that here that I could just plug into these locations. When your circuit is working, you'll see that, well, I happen to have high resolution here, that it's pretty sensitive. I'm clenching my muscles now, and you can see that the circuit is responding to those clenched muscles. The shape of the wave happens to depend on where you have the electrodes connected. I happen to have 2 up on my upper chest and 1 down on my lower right abdomen.